Thanks for the short introduction. So my name is Thorsten Kurth, and what I'm going to present today is a project I'm doing with my colleague David and colleagues from ECMWF, namely Patrick and Peter. And I will talk about the 3D bias correction using deep learning for the integrated forecasting system. So what is the problem? So ECMWF is developing their own atmospheric model, which is called Integrated Forecasting System, or IFS. And like all the models you know, it has a systematic uncertainty. And it turns out that these are largest between like 15 and 40 kilometers. So these are like correspond to level indices in the model of 20 to 65. So what can you do here? You can improve the situation by first gathering more data, and that you can do by, for example, using sound balloons or a technique called radio occultation, which I'll explain very briefly. So what you have here is you have a GPS satellite in some high orbit, and then a LEO, so low Earth orbiting satellite, receiving signals from this GPS satellites, radio signals. And then what you do is observe the bending angle between these satellites. And as the LEO progresses on his trajectory behind the Earth, you can basically get a profile in terms of like bending angles, and from that you can infer the temperature of the atmosphere. So it turns out actually that the precision of this now is pretty good. It's like similar to conventional probes, but the coverage is much better. So we want to use this data to improve the model. And this is traditionally done using a V-constrained 4D VAR. So you have basically a prediction, like from the IFS model, for example, and you want to subtract the thing which is called the bias. This is this offset here. And what you see here is this blue line, which is the model prediction. And then when you plug in the data at these different observation points and minimize this fitting function here, you basically extract this bias and use this as an initial condition or like add it to the model state to get a better initial condition for the next step. And what we want to do is develop a deep learning model which basically approximates this bias already. So like it improves the bias in the sense that once you apply 4D VAR to the corrected bias corrected model, the new bias will be much smaller. So generally, V-constrained 4D VAR is pretty good. So what this shows is like the bias over time. So it's an online learning approach, right? Because you correct the model as you go. And as you can see, it's pretty good at actually learning the model bias, and it decreases over time. So this is actually a pretty hard target to match. So and the approach we want to develop should at least be as good, if not better. So this is the data set we have. It comes from this GNS-RO observation. RO stands for radio occultation. I think in the past it's called GPS-RO, but since this like involves now other satellites like GPS GLONASS and Galileo, the name changed. And the data is quite recent. So there's high quality data since 2007. And what we are using here is data from 2008 till 2021. So we don't have a wealth of data, unfortunately, but we have some. And what we do is we train on the ensemble of from 2008 to 2019 and 2020 plus. So 2020 and the first half of 2021 were basically reserved just for testing. We also want to see, so since the data is pretty spotty and noisy, we want to also apply some averaging or data smoothing. So we can average, for example, over 2 days and 10 days, so in time, or over a space, so like 2 degrees or 10 degrees, for example. So we try these different possibilities in order to get an estimate of what is better. So this is the data set. This is a short visualization of it. So what you can see is the vertical cross-section in the upper row and the horizontal cross-section in the lower row. So the first and the third columns are the raw input. So you see these white lines and the missing data. This is basically from missing observations and from the projection itself. And then the second and the fourth column represent interpolated input. So if you average the data over long enough times, it's not very sparse. So the interpolation might be very stable. But I will come to that we want to relax this a little bit. So and what you can see here is basically the profile, and you see that you have some features in the data, and the neural network should be able to pick this up. So on the left-hand side, the left two columns are the input, and the right-hand side are the output, which is in this case the bias. So this is just the bias. So we learn just the model bias itself and not the model value plus bias, because learning a bias is usually easier. So you can also look at time series of this data for different latitude regions. And what you can see here is there are a lot of features you need to learn. So for example, there's a positive correction below level 30, but the negative correction above level 30. So that's important to pick this up. There's also this quasi-biennial oscillation. These are these green spots here. So these are these kind of spiky patterns of a negative correction, and it actually propagates down in time. So it's like it's variable in time, but it's a feature. It's not like statistical noise. And the other one is this sudden stratospheric warming events, which are these spikes in the data where you basically have these kind of like negative bias corrections, like going further down. So this is important to so that the neural network needs to learn this in order to be good. So a little bit more technical details about the data set itself. So it's a NumPy format. It's pretty easy to use in Python, in deep learning frameworks. So we use 2 resolutions, averaged over 10 days and 10 degrees in space and time, or 2 days and 2 degrees. And you see the difference here. So like the image size is much different, of course, but also like the sparsity. So when you look at the upper 4 plots, those are 2 different levels or altitudes at the low resolution. So the sparsity is like 97%. So like most of the pixels actually there. But then when you go down on the lower part, this is 2 day, 2 degree. It's like 30% sparsity. So basically most of the image is not there. Of course, when you look at the time series, since the satellite move, they basically fill out the missing gaps. But for a single snapshot, you do not have a lot of information. And we interpret the data in a 3D fashion. So we have a longitude, latitude mapped onto basically onto an image. So we heard in the last couple of days that there are other methods now, and I'll come to those later. But in general, so this works well for like a first exploration. And so we have, as I said, 3-dimensional features, latitude, longitude, and the altitude, and just one feature, because all what these satellites can measure is temperature, unfortunately. So this is the network architecture. Since we want to map an input image or input volumetric image to an output volumetric image, it's a segmentation or like a image regression-based model is suitable for this. And we use DeepLab version 3 Plus with modifications and use an exception backend in the encoder. So how does this work? So we have this input, we pipe it into the encoder. From there, you go into this ASPP layer, which is called atrospatial pooling. And what it does, it extracts at different length scales, different features, which can be fed into the decoder. So on the right-hand side, the model sketch you see is for a 2D model, which was used for a different project before. So, but I think you get the general idea, because plotting this model is a bit messy. And then you have the decoder part, which will basically use this information from different level features. For example, you see these skip connections here, which come like out of the decoder halfway and go directly into the decoder. This should help to learn features at different length scales and to get a better reproduction. So the decoder is completely convolution-based or transposed convolution-based. And we use average pooling in the upsampling part, because there are some, otherwise you will get some checkerboard artifacts. So this is just a technical detail. I don't want to talk about this, but you can basically suppress these checkerboard artifacts by doing these tricks. So since this is a regression problem, we can use several different loss functions. There's just like the L1 norm or L2 norm, or like the smooth L1 norm between the input, the output of the network and the target. And they have all like different like advantages and disadvantages. For example, L1 this continues in 0, but penalizes every deviation like linearly. Whereas L2 is pretty good of penalizing outliers, but not very good when you have like small deviations. And the smooth L1 is basically just the smooth matching of these two. What we want to do is definitely take care of the holes or like the missing data. So what we do here is that we reweight the pixels, which are interpolated. So that means we split the loss in two parts. So we do not drag around only the prediction and the target, but also a mask. And the mask basically tells you, it's a binary tensor, which tells you which pixel is actually interpolated and which pixel actually exists in the data. So and by that, we can basically determine a term of the loss for the valid part. This is abbreviated with this coefficient lambda v for valid, and the whole part, which is abbreviated with lambda h. And we can give different weights to these two parts. And in our case, we use 1 and 0.8. So that basically the network will learn to not look at these interpolated pixels too much. So you can change this ratio also, and we played around with it. It's technically hyperparameter if you want. We also need a loss like a score metric. So they're not like, I mean, there's no like canonical one you can use. So that true score is pretty okay. So what it basically does, it measures the quality of the predictions against intrinsic noise. And the way it's defined here, score smaller than 0 means you have very bad accuracy. So it's like, yeah, guessing. So score around 0 means your predictions are consistent with the model noise, which is with the noise in the data, which is also not very good. And if you are close to 1, or like everything significantly close to 1 is actually very good. And we use this as evaluation metric, not as training criterion, although you might see that if you look at the L2 loss, it's basically the numerator of this fraction here. But I have to say that actually it's not when you do hyperparameter optimization of this problem, the L2 loss networks, or the networks minimizing the L2 loss, do not perform necessarily the best. So that is still like open. So it's definitely nice to have this score, because then you can compare different losses to each other. So this is just the convergence plot. So this is the R2 on the validation sample for plenty of runs, like collected with weights and biases online. So I don't come up with the names, they're auto-generated, so they're funny sometimes. And what you can see here is that it's pretty stable. So most of the networks generate R2 value of 0.5, which is pretty decent, I think. And over a wide range of hyperparameters, you actually get a pretty good convergence. So this network is pretty stable. And we only see light overfitting, although we have only 400 training samples available for the 10 days, 10 degrees. So it's pretty stable. And then you can go in and then qualitatively select the best, the models, or like the models with the best convergence curve you like. So that is like up to you. So this is the prediction quality for 10 days, 10 degrees. What you can see here is the left columns, which set a predicted model error, is the output of the network, and the calculated model error is the one from the fits or target. And on the right-hand side, you also see these cumulative density functions. These are like a zero-order metric, if you want, and basically compare the pixel intensities of the prediction with the target. And you see them match pretty well. So at least this test is good. And what you can see here, that certain features are actually pretty well learned, right? So like these negative bias spots, these positive bias spots in the negative bias region, and also these bands here. Right, so this is pretty good. So when you look at the 2-day 2 degrees, it holds up actually. So although here most pixels are interpolated, actually it seems that the neural network does a pretty decent job on this. So I don't want to point out different parts here, but you see that qualitatively they agree very nicely. So even here the neural network can produce noticeable features from the data. So now you can also look at the time series. So first I want to apologize for the colors. So they are very similar. It's just that on the left-hand side in the post-processing, I screwed up the normalization. But it's so, like, believe me, they are similar. So, but what I want to point out here is that the prediction and the target, you see these features also in this time series. Like here, for example, this positive bias in the negative bias region, this very positive bias here, and for example, this other positive bias spot here. So like so the network learns over time, although we do not have temporal dependence in the model, it learns these features nevertheless. So as a summary, so the proposed neural network is learning the model bias. And gets like the features right. So that can be used, for example, to correct the initial conditions in the data assimilation pipeline. You can also do sensitivity studies to learn more about your model bias at all, right? So we haven't done this yet, but this might be like a future thing to do. There's a trade-off. It's unfortunate. You want to have high resolution, but then you have a lot of noise in the data, or you have low resolution, less noise, but yeah, then you have low resolution. And for this, in terms of sparsity, so when you go to the 2-day 2 degrees, it's already really sparse. So the masking still works, but you might want to try different approaches. So we are looking into approaches like graph to image, for example, where you start with a data representation which is like a sparse, like a graph, and then you map this to like a full graph, like an interpolated graph if you want, using your preferred spherical data. And so that is something which we also want to look into. And most importantly, we want to feed this back into the full data data assimilation pipeline. And here the problem is that quite tricky, because when you correct the bias with the deep learning model, then the next model bias will be and then you apply the model to the corrected input state. The next bias might be smaller, but the neural network you trained assumes that the bias is uncorrected, so you might overpredict. And that can become unstable. So we are currently looking into how to alleviate this issue. So this is the next big challenge in this project. So thank you very much, and I'm taking questions.